The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome to the channel Statistica Hub. So as we have started the course of Bayesian inference, and as it is an open course, and we have already uploaded the introductory lectures corresponding to it, and in that lecture we have discussed that in what problems we can use the Bayesian inference, the very basic things like what is a prior and all these things. But don't worry, we will be discussing all these things in the upcoming parts and in very detail. Okay, so for understanding the concepts of Bayesian inference, the very first thing that we need to do is to understand the basics of probability. Okay, if you know the concepts of probability theory, it's a plus point for you, but if you don't know, then take a relief. We will be discussing all the concepts of probability theory that we are going to use in the Bayesian inference. Okay, so yeah, let's start with it. So for understanding the basics of the probability theory, okay, the very first thing everyone asks is like, what is a probability? Okay, and I'm also going to ask you the same thing, nothing new. But yeah, the new thing is that you are always seeing the probability as just like probability in the frequentist approach. Like, I am having this much number of outcomes, I am having this much favorable outcomes, and I'll divide these, I'll get my probability. But now the only thing that you need to change the thinking. Okay, that think the probability from the Bayesian point of view. Okay, so if you try to think the probability from the Bayesian point of view, that will be very easy for you to understand then. Okay, so yeah, the concepts are basically, the basics are similar that we are going to use. We have already studied that what is probability, what is classical probability, like what is frequentist approach to probability. You must have studied all these concepts before. If you haven't, I'm going to discuss all these concepts in this lecture 1. And so yeah, but the only thing that is required, that how these concepts are like applying in the Bayesian inference. Okay, so yeah, talking about the probability, as I mentioned that I will ask you the same question, that what is probability? Okay, so probability is simply, if I define it, it is how likely something is to happen, right? Okay, and we calculate the probability corresponding to some events, right? So whenever we say that we are trying to find out the probability, we are actually talking about that we are finding the probability corresponding to some events. Okay, let's say probability of event E. Okay, now talking about the events, we can have impossible events, certain events, okay, and whenever we are having uncertainty. Okay, so we are going to discuss the probability of the events in these cases. Okay, so let's talk about the impossible events. Impossible events, like if I just give some example, that what's the probability of a married bachelor? Like, what's the probability of a married bachelor? Now you know that the person who is already married, he can't be a bachelor, and if he is bachelor, then he can't be married, right? So the probability corresponding to this event would be 0, because this is an impossible event. Okay, now certain events. Now let's go back to the philosophy part. Okay, so every human being, every living being, for every living being, if I ask what's the probability of death, everyone who has taken the birth is going to die one day. Okay, There is no one who is going to be immortal. So the probability of death is going to be 1. This is uncertain event. Okay, sure event that it will happen someday. Okay, and whenever we are having an uncertainty, that I want to know that what is the chance of the particular event happening, then we are talking about probability. We are calculating probability. We are measuring uncertainty in that case. So in that case, our value would lie between 0 to 1. Okay, that's a very basic thing, that my probability would lie between 0 to 1. Now, probability is the foundation, very basic foundation in studying statistics, right? And the probability has been, that the definition corresponding to probability has been improved from time to time, right? And the very first basic definition we study about the probability is the classical view of probability. Okay, and in this classical view of probability, we say this, that if a random experiment is performed and this random experiment has total n outcomes, and these outcomes are coming out to be mutually exclusive, exhaustive, and equally likely. Okay, so if there is a random experiment which has been performed and there are n possible outcomes corresponding to it, and these n outcomes are mutually exclusive, mutually exhaustive, and equally likely. Okay, so that means equally likely means that the probability of each outcome is going to be same. Okay, or here, as you are having n outcomes, so the probability of each outcome is going to be 1 by n, right? So in this scenario, when you are having a particular experiment satisfying these three conditions, then at that time you would say that the probability corresponding to some event E of happening is going to be m by n, where m is the favorable number of cases out of n outcomes. Okay, and n is the total number of possible outcome of random experiment. Okay, now in this classical view of probability, you can see that there are some specific conditions that needs to be satisfied for this probability to occur, and the conditions has to be that the outcomes has to be mutually exclusive, exhaustive, and equally likely. So it has its own limitations, and the limitations we can see in the definition. Okay, so if we are talking about the limitations here, its limitations are basically the first thing, that if the outcomes are not equally likely, okay, it's not possible that if I'm having n outcomes and they are all equally likely. So there are many cases where the outcomes are not equally likely. Okay, if outcomes are not equally likely. Second case is if the total number of outcomes of some random experiment is maybe unknown. You don't know that what is the total number of outcomes, you can't find that out, or if it is going to be infinity. Okay, now if there is going to be infinity, then you know that the probability of certain event is going to be 0. Okay, that is not the accurate estimate of probability, because there are some favorable outcomes corresponding to that event, so probability has to be something. It can't be 0 in that case. Okay, so these are two limitations corresponding to it, and because of these two limitations, there is new definition arises, okay, that overcomes the limitations of the classical probability. Okay, and this new new, or you can say revised. That is said to be the frequency view of probability. Frequency view of probability. And this frequentist view of probability is related to the relative frequency. Okay, relative frequency. Okay, now in this view of probability, we say that if a random experiment, if an experiment is repeated under identically homogeneous conditions, okay, then the limiting value, okay, then the limiting value of m by n as n tend to infinity is going to be the probability of the event E in n independent trials. Right? So this is the frequency view of probability, where this m by n is the relative frequency here. Relative frequency. This is not similar to what we have studied here, m by n, because this m by n is related to when we have considered that the outcomes are equally likely. Okay, but in the frequentist view of probability, there is no boundation that my outcomes are going to be equally likely. It can be either case. If they are not equally likely, then it is okay. Okay, so here m by n is corresponding to relative frequency of the outcomes. Okay, and we are finding the probability for n is tending to infinity. Now again, the limitation of this probability is lying in the definition. Okay, so what's the limitation? If I just note the limitation, then the very first thing, we have studied the concept of limits, right? And there is a possibility that the limit of the particular cases would not exist. Okay, so the first scenario here is that maybe that the limit may not exist. And the second scenario, it is saying that you have to perform a random experiment under identically homogeneous conditions. Okay, which is not possible each and every time. Okay, when it is not possible to repeat the experiment, or not possible, let me write, not possible to repeat the experiment, or you can say that maybe when you are repeating the experiment so many times, then the experimental condition may not remain same. This is the second case. Experimental condition not same. Okay, because I will give you some example where it is not possible to repeat the experiment. Just hold on a bit. Okay, so yeah, this is a frequency view of probability. Okay, and that was the classical view of probability, where we are considering the outcomes to be equally likely. Okay, now let's take some example that we always say that the probability of head is 1 by 2, probability of tail is 1 by 2. But who told you this? How do we get to this conclusion that the probability of head or tail is 1 by 2? That is actually related to the relative frequency, or you can say frequentist approach. The second thing we have studied is actually related to, we say this as frequentist approach of probability. Okay, so let's take an example. When we flip a coin, okay, and let's say we are flipping a coin which is 10 sets of 1000 coins. Okay, so I have 1000 coins, and I'm going to toss those 1000 coins 10 times, like these bunches of 1000 coins, and 10 times. Okay, so let's say I'm throwing this 1 2 3 to 10 times. Okay, and in one time we are throwing 1000 coins, and we are noting the x, where x is the outcome for head, that is total number of heads. Okay, so let's say I'm just taking a random number right now, that if I'm tossing 1000 coin in a very first time, then maybe I'll be getting a number like 502. and the second time I'll be getting like 407, or maybe like 497. Here I'll be getting 520. Anything we can get in all the 10 sets, we are getting some different outcomes. Okay, now when we are now what do we want to calculate? We want to calculate the probability of head. So when you have done the experiment so many times, you have performed the experiment 10 sets of 1000 coins, that means you have taken, you have what is the total number of possible outcomes that you can have? 10,000, right? And the total number of outcomes that you are getting, you can add all these and you can get the total number of outcomes. That will be something. Okay, and this thing is going to be 1 by 2. Okay, this thing is going to be 1 by 2. So when we are thinking about a fair coin, whenever we say that I'm tossing a fair coin, we are actually talking about long term relative frequency. Long term relative frequency, that means when we say that the probability of head is approximately 1 by 2, we actually mean that the long term relative frequency of getting heads is going to be 50% or 1 by 2. Understood? That's the main reason why we say that the probability of head is 1 by 2 or the probability of tail is 1 by 2. Okay? Okay. Now, in this scenario, let's try to consider an example. Okay? Okay. Let me consider another page, or maybe just here. Let's say we have 3 tosses. We are doing 3 tosses of coin. Okay? And when we are doing 3 tosses of coin, we are getting 3 tails. Okay? And if I ask you in this scenario that what is the probability of head? What is the probability of head? You would just simply say, then there is no reason to ask right now because the probability of head is going to be 0. Right? You're right. The probability of head is going to be 0. But in this case, you are calculating the sample percentages of heads. You would say that you are calculating the sample percentages of heads is equals to 0. Okay, but this can't be an accurate estimate of true percentage of heads, because we know the prior knowledge we have is, we always study this, that the probability of head is approximately 1 by 2, is 1 by 2. But here the probability of head is coming out to be 0 because we are calculating the sample percentages of heads. So when we say that the probability of head is 0, we are actually saying, this does not mean that the long term probability is 0, but it is saying that we haven't performed the trial long enough time. We have just tossed the 3 coins. Okay, so that's why the probability of head is coming out to be 0. If we increase the number of times we are tossing the coin, then the probability of head will be approximately 50%. So it means that the flipping is not long enough. Is not long enough. Try to think like a Bayesian point of view. Bayesian point of view. Okay. So, in the classical point of view, in the classical building, the classical approach or the frequentist approach is based on the assumption that we will be able to repeat the experiment a larger number of times. Okay, and this scenario is not feasible in so many cases. Okay, that we won't be able to repeat the experiment a larger number of times. Okay, now let's see the next thing, that is axiomatic view of probability. Okay, I don't like this pen, let me change it. Axiomatic view of probability. Okay, so in the axiomatic view of probability, this view of probability is related to the functions and the set theory. Okay, it is related to function and set theory. So just like the functions, in the functions we always say that there is a function f which is defined on some domain to some range r. Okay, similarly here we consider the probability as a probability function. We would say that probability of a is some probability function. It is some probability function which is defined on some domain to range r. Now the main point is, what is the domain and what is range? The range, we all know that if I calculate the probability, my range is coming out to be between 0 and 1. And the domain is actually the sigma field. But what is sigma field? Right? We always say that my domain is sigma field. So my sigma field is defined to be a non-empty class of sets. A non-empty class of subsets of sample space. Subsets of sample space S. Okay, that satisfies some properties. And what are those properties? First thing, that non-empty class of subsets, let's say that class is defined as B, okay, which is subset of S. Now this class of subsets B is going to satisfy some certain properties. The very first property is that is closed under the complementations. That means if A is any set which belongs to this set B, this means that the complement of this event A is also going to belong to that B. Okay. And second thing, closed under unions, closed under countable unions. Okay, countable union means that if I am having certain AI, so many possible number of outcomes which are belonging to B for I is equals to 1, 2, 3, okay, countable unions, then the union of all these events, infinity, would also belong to this set B. The third thing, that null event phi would also belong to this B. So when we are talking about a sigma field, we are actually talking about a set of the sample space, a subset of sample space which is satisfying these three properties. That is my sigma field. Okay. So in the axiomatic probability of view, we say that I'm having a probability function which is defined on the domain sigma field and on the range 0 to 1. Okay. So if probability of A is defined under certain conditions and under certain axioms. Okay, if the certain axioms hold, okay, yes, firstly, yes. So if the certain axioms hold, then we can say that probability of A is a probability function. Okay, and what are these axioms? The first axiom is, for each A belongs to B, probability of the certain event A is defined. Second thing, probability of the whole sample space S is equal to 1. Third axiom, if you are having AI, which is certain events, a sequence of events which are disjoint, then the probability of union I is equals to 1 to infinity of these AI is equal to summation I is equals to 1 to infinity of probability of AI. And these axioms have certain names. The first one is said to be the axiom of non-negativity. Non-negativity. Okay, that means, one more thing. Probability of A is greater than or equal to 0 in the first one. Second one says axiom of certainty. Certainty. And the third one says axiom of additivity. Additivity. Okay. And these axioms are going to be used in defining the upcoming parts. Okay. I think there will be no doubt here. Let's go further. Now let's try to consider one example. Okay. Now I just now remember that I think IPL is going on in India. Okay, Indian Premier League for those who don't know. So there is an Indian Premier League going on for cricket in India, and suppose we are interested in the probability of winning of a particular team. Okay, so as let's say there are 10 teams. There are 10 teams there. Okay, and we are trying to find out that what is the probability of event that Mumbai Indians Mumbai Indians Mumbai Indians will win the trophy, will win the IPL trophy of 2024. Okay, and don't get offended if you like any other team, like maybe Chennai Super Kings or Delhi Devils. You can just replace it there. You can just find out the probability of the event of winning Chennai Super Kings of this IPL trophy. Okay, so I'm just calculating. This is just an example that what will be the probability of event that Mumbai Indians will win the IPL trophy. Okay, so for this scenario, if there are 10 teams who are going to compete, now if we say that each team has an equal chance of winning, okay, that is not true. Okay, if we say that each team is a possible winner of a trophy, then it is not true, because the events are not equally likely in this case. We are saying that the events are not equally likely. Okay, so the probability of winning of each for each team is not equal to 1 by 10. Okay, because the reason behind it, because some teams are stronger than the others. Like there is a IPL, so you always have some prior knowledge in your mind that this is a strong team, this is a weak team, right? You have that knowledge in your mind, so the probability is not same for each of them. Okay, so the very first scenario, the classical approach to probability fails here, because in the classical approach we need to have an equally likely events, equally likely outcomes. Okay, so classical approach won't help here, won't help. Okay, now consider the second scenario. Now the probability, the event that the Mumbai Indians will win the match is a one-time event, is a one-time event. And why am I saying it is a one-time event? Because we cannot repeat this experiment, can't repeat this experiment under identical conditions, under identical conditions. Now you must be thinking that why can't I repeat it, because Mumbai Indians is going to play in the next match. Okay, but the conditions are not going to be similar in the next year match. Okay, because the reason behind it, because maybe in the next year players in the team would change, maybe the corresponding matches that are happening right now, the opposition team would change, or maybe if the opposition team remains same, then the opposition team's player would also change. So accordingly it won't be the same match as it is happening right now. The conditions would not be identical. So here the frequency twist view, the frequentist view also not hold, is not helpful. Okay, but there is one more thing, that is the Bayesian approach. So Bayesian approach is basically, we are talking about, we are talking about Bayesian approach, that is basically we are talking about subjective view of probability. Subjective view. So subjective view is basically, it represents the person's belief in likelihood that his or her team will win. Like what I think that the Mumbai Indian will wins, that's the probability, that's different. Let's say I think that there are 80% chances that the Mumbai Indian will win, but there is another my friend who thinks that there are 70% chances of it. So the subjective view depends on the person to person opinion. Okay, but yeah, this information is very helpful in the Bayesian approach. Okay, and we will see how we are going to use, that is the main thing in the Bayesian approach, to use the information in this way to get the conclusion regarding the outcomes what we are going to consider. Okay, so in the probability and in the statistics there is a very main difference, what we do in the statistics and what we do in the probability. Okay, it just when we calculate something or when we do probability is just, you can say, it is a forward problem, or statistics you can say it is a inverse problem. So why am I saying this? Okay, you can understand this by an example. In the probability, whenever we calculate it, we assume we know how the data have been generated and we calculate the probability corresponding to it, right? Like for example, we say, like, what's the probability of flipping 5 straight heads if the coin is fair. Okay, now it is, the information is already given that the coin is fair. You are throwing 5 coins, so you have the corresponding outcomes, so you know that what is the data. Now from that data you just have to calculate the probability. Okay, so in this probability problems we already know that how the data have been generated, how the data have been collected, but the statistics is just the inverse of it, because in the statistics we use data to learn about data gathering mechanism. Now in the same 5 flipping coins, we can, if I just change the scenario, like if we'll ask the question like this, that if we flipped 5 straight heads, can we say the coin is biased? So in the first scenario we are talking about that the coin is fair and we have to calculate the probability of 5 straight heads, and in the second scenario we are saying that I am having 5 straight heads, can we say that the coin is biased? Okay, so they are just the inverse problem of each other, so try to differentiate between them. We use the probability in the statistics, but statistics is basically just the inverse of probability. Okay, so yeah, in the statistics the main part is to understand the data, that how the data have been generated. Okay, and we use that when we are taking the samples from the population, we are trying to understand the data. It is all about the data. Okay, now let's talk about the other things, that the conditional probability. Okay, now conditional probability is the main foundation for the Bayesian inference. Okay, talking about the conditional probability, it just says that if we have a prior information that the outcome of random experiment must be in a set B, which is subset of S. Okay, that means there is a sample space S. Okay, and this is the subset of, this is set B. Okay, so we are having a prior information that the outcome of random experiment is going to be in B. At that time we would say that the probability of happening of some event A, given that I know that the B has already occurred, is going to be probability of A intersection B upon probability of B. Okay, and here the probability of A intersection B measures the degree of belief, in A, if given that B is true. Okay, so this is the degree of belief corresponding to A when the given information is that B has already happened. Because now our interest lies in those elements of A which are part of B, not the whole sample space. So we have actually reduced our sample space now. Okay, and there are some remarks here, remarks, or you can say the other properties corresponding to the conditional probability. The very first thing, that if you are having two events A and B, for them the probability of A is greater than 0, probability of B is greater than 0, then probability of A intersection B is equals to probability of A into probability of B given A, or probability of B into probability of A given B. So this is actually the multiplication rule of probability. Multiplication rule of probability which says that the simultaneous occurrence of two events A and B is equal to the probability that A has happened product to the second probability that B has happened given that A has already occurred. This is simultaneous occurrence. Okay. Second point, that if you know that your probability of B is greater than 0, then probability of A given B is less than equal to probability of A. So as we are reducing the sample space, now my main concern is only those points of A which are in B. Okay, so we are reducing the sample space. This probability we have calculated on the whole sample space. Now we have reduced the sample space to B. Okay, so the corresponding probability would also reduce, and the reason behind it, because favorable number of outcomes in n of A intersection B is basically less than equals to n of A, total numbers. Okay, similarly total numbers in B is less than equals to total numbers in S. Okay, and dividing these two equations, we got like n of A intersection B is upon n of B is less than equals to n of A upon n of S. That's the reason we say that the probability of A given B is less than equals to probability of A. Okay, and yes, we can generalize this result for n number of outcomes. So like here we have just finded this out for the two events. I'm sorry if I'm repeating the outcomes again. So let's say if you are having A1 intersection A2 going on till intersection AK. Okay, we are generalizing the result of multiplication rule of probability. Then this can be written as probability of the happening of event A1 into probability of happening of event A2 given that A1 has already occurred, probability of happening of event A3 given that A1 and A2 has already occurred, and similarly going on, probability of happening of event AK given that all the other events except AK have been occurred. Okay, that's the generalization. Okay, now as we have defined the axioms corresponding to axiomatic theory of probability, now as we are saying that the conditional probability is the main foundation of the Bayesian inference, so to provide a solid theoretical foundation, we are going to define the axioms corresponding to conditional probability. Okay, so here we are going to say that probability of A given B is our probability function, okay, which is defined on some domain and range. And because we are going to have some theoretical foundation, a solid theoretical foundation, so we are going to assign the axioms corresponding to it. Okay, and this probability function is going to satisfy some properties that are said to be axioms. And the very first thing, that the probability has to be defined. This means probability of A given B is greater than equals to 0. Second thing, probability of B given B is equals to 1. Now it is very easy to say. See that if I open the conditional formula, it is going to be probability of B intersection B upon probability of B, and intersection of the event from that particular event is going to be probability of B. So it will be probability of B by B, that is equals to 1. Third thing, that probability of union j is equals to 1 to infinity of aj given B is equals to summation j is equals to 1 to infinity of probability of aj given B. That is the additional rule. This is like you can see, this is axiom of non-negativity, this is axiom of certainty, and this is axiom of additivity. Okay, but there is one more axiom that is needed in the conditional probability. That axiom is the multiplication rule for probability. That if we are saying, that is actually derived from the multiplication rule. So this axiom is that probability of for three events A, B, C, we say that probability of C given A intersection B into probability of A given B is equals to probability of A intersection C given B. Okay, and this is derived from the multiplication rule of probability, which is, let's say if I'm having three events and we are finding the simultaneous occurrence of these three events, that is A intersection B intersection C. So we are just saying that probability that B has already occurred into probability of happening of event A when B has already occurred, probability of happening of event C given that A and B has already occurred. Okay, now if I transfer this here, it will be probability of A intersection B intersection C upon probability of B, right? And which is equals to probability of A given B, probability of C given A intersection B. That is equals to probability of A intersection C given B is equals to probability of A given B and probability of C given A intersection B. Okay, so that is just the reframing of the simultaneous occurrence of three events. Okay, so these are the corresponding four axioms related to the conditional probability. Okay, I think there is no doubt in this. Okay, and next thing that we are going to do is the law of total probability. Law of total probability. Okay, so the law of total probability says that if you are having a countable collection of mutually exclusive, if you are having these sets which are countable collection of mutually exclusive and exhaustive events in sample space S. Okay, and the probability of each of these events is defined, but as they are mutually exclusive, that means probability of AI intersection AJ is equals to 0. Then if there is an event B, okay, which is where B is actually the union J is equals to 1 to infinity of B intersection AJ, that means the scenario would be like this. If I draw a graph corresponding to it, then it will be like this. My drawing is quite bad, so spare me for that. Okay, so let's say this is A1, A2, going on till like kept on going. Okay, other events A3 and other events. Okay, and B is the simultaneous occurrence. B is the intersection of all these events. So B would be like this, happening with all these events. This is the event B. Okay, so B is union of B intersection AJ. Okay, so that means the law of total probability says that the probability of B is equals to summation of J is equals to 1 to infinity probability of AJ probability of B given A J for all B, which is the subset of sample space S. So S is the whole sample space, B is the set of it, and if I open it, this means that probability of the happening of event A1 into probability of happening of event B, given that A1 has already occurred, that is the probability of this portion. Now second, probability of happening of event A2 and probability of happening of B, given that A2 has occurred, that is the probability of this portion. So simultaneously going on like this, we are adding the probabilities of all these events. So by doing this again and again till infinity, we will get the total probability for B. Okay, so yes, now these are the things that we have seen today. Okay, and yes, and one more thing that I remember now, right now. So the probability, when we are talking about the probability, we are seeing the probability in two ways. Talking about probability, we are seeing the probability in two ways. The first one is objective. Objective is basically the classical or the frequentist view of probability. And the second one is objective, and the objective is related to the Bayesian view of probability. Okay, so in the objective view of probability, we see the probability of some certain event X as a purely mathematical statement. Okay, that it will satisfy some properties. It is having likely outcomes, equally likely outcomes. It will satisfy that n is tending to infinity, all these things. Okay, so it's a purely mathematical thing. Purely mathematical. Oh my god, my writing is too bad. Probability of X as a purely mathematical statement. Okay, and in this, the probability is actually defined as long run relative frequency of repeatable events. Okay, and that is probability of A is equals to limit n tends to infinity of m by n. And in the objective view of it, we are seeing the probability which represents, here the probability represents as a degree of belief, individual's degree of belief. Okay, and as we know that two people could have different beliefs, right, depending on my opinion and other person's opinion. So basically when I'm saying that the opinions would change so the probability would also change, this actually means what I'm trying to say is this, that probability changes as we gather new information. Okay, this is the main thing happening in the Bayes theorem. We are gathering the new information, we are updating our probability. So this will going to happen continuously as we are gathering new information. For example, if you are having a certain opinion about a particular team, that the team has performed very well in the previous matches. Okay, you are having that opinion by like considering those previous matches. Okay, but then someone told you that the players that scored well in the previous matches, the good players are not playing in this match. Okay, then you updated your information by the information that you have just received. Okay, then After receiving this information, your probability of winning for that particular team, what you were thinking, would change now because of that new information. So in the Bayesian, you are continuing to gather new information and then you are continuing to updating your beliefs according to that. Okay, so yeah, talking about the Bayesian thing, what we are going to do, there are three main blocks when we are studying the Bayesian inference. Okay, and what are these three main blocks? Three main blocks. That is, the first thing is modeling. We are going to do modeling in the Bayesian inference. The modeling is basically including prior knowledge. In the classical or frequentist approach, we don't do that. Okay, we don't include prior knowledge. So include prior knowledge, or you can say expert's opinion. Okay, the second thing is theoretical. So as we have seen in the classical approach, we need to do the random experiment a large number of times. That is not the that is not the requirement here. There is no need to have large sample assumption. Does not need large sample assumption. Sample assumption. Okay. And the third thing is computational. So in the computational, like how to compute the estimates or the other things, that is, we are going to use Markov chain Monte Carlo method, MCMC, the Gibbs sampler method. These are the main computational techniques that we are going to use for complicated models of the Bayesian inference. Okay, now so these are the main things that we are going to do: modeling, the theoretical concepts, and the computational concepts of the Bayesian inference. So the first thing that we are going to study right now, or like not right now, in the upcoming lectures, is basically understanding about the prior knowledge, that how to use that prior knowledge in mathematical point of view to get the to revise the probability or to get the revised results. Okay, but there is one more thing that you need to notice, that when you have large samples, there is no requirement of large sample in the Bayesian approach, but when you are having a large sample in the Bayesian also, then both the approaches, whether you are applying Bayesian, whether you are applying frequentist, they both of them for the large sample arrive to the similar results. So there is no problem. For the large samples, they both are going to give you the same results. Okay, so yeah, that's it for this lecture. We will continue the basics of probability. Like I think we are going from the very basics. We have just defined the probability. We have discussed all the axioms and definitions of the probability. We will continue this portion in the upcoming lecture 2. Okay, and in that we will also define some distributions, univariate and continuous distributions, discrete and continuous. Sorry. Okay, then have a nice day, and yes, thank you so much.